Canucks LRD Z8.6 is not just another faint red smudge in a Webb image, not a normal young galaxy, not a harmless dusty spark, but a system that may already be feeding a monster black hole only 570 million years after the Big Bang. That is the crisis. Not whether the object is interesting, it is. The real problem is time. The universe was still in its cosmic childhood. Stars had only recently turned on. Galaxies were still assembling their bones. And yet this little red dot may have built the kind of dark engine we usually expect after much longer histories. Think about what that means on a human scale. It is like walking into a town where the concrete is still wet. The streets are half paved, and somehow there is already a fully running industrial furnace in the center. The buildings are unfinished. The smokestack is not. What Webb found in these little red dots is a class of compact, unusually red, very early objects that seem too bright, too dense, and too mature for their age. Canucks LRD Z8.6 may be one of the clearest examples because the light appears to carry the fingerprints of an active galactic nucleus, which is a polite way of saying matter may be spiraling into a central black hole and heating up as it falls. Heating up. In 2024, a team led by Marin Franks and collaborators reported evidence that this object sits at redshift 8.679, placing it roughly 570 million years after the Big Bang. They estimated a black hole mass on the order of millions of suns, with a host galaxy whose stellar mass may be only around 10 to 100 times larger than the black hole itself. That ratio is the unsettling part. In nearby galaxies, the central black hole is usually a much smaller fraction of the whole system. So the what is simple. This may be a very young galaxy whose central black hole grew absurdly fast or was born unusually heavy before the galaxy around it had time to become normal. The how is where the story gets uncomfortable. Under the standard picture, you begin with the first stars. Some die and leave behind black holes with maybe tens or hundreds of solar masses. Then those remnants feed, merge, and slowly grow. Slow is the dangerous word here. Even if a black hole grows at the Eddington limit, which is basically the fastest steady pace before its own radiation pushes infalling gas away, the clock is brutal. You need repeated doubling times, little interruption, and a supply of gas that behaves with almost suspicious obedience. And space is not obedient. Gas gets heated, stars explode, radiation shoves matter outward. Young galaxies are messy places. Growing a black hole there is less like filling a tank and more like trying to drink through a straw in the middle of a hurricane. That is why astronomers have been considering another route: direct collapse. Instead of starting with a small stellar remnant, a huge gas cloud in the early universe might avoid fragmenting into many stars and collapse into a black hole seed of maybe 10,000 to 100,000 solar masses. David Whalen and other researchers have explored how this could happen under intense radiation conditions that suppress normal star formation. If that route works, the universe did not grow every giant black hole from a tiny ember. Some may have started as bonfires. Personally, I think this is the part that changes the emotional tone of the whole story. We are used to imagining the cosmos as gradual, patient, layer by layer. But These early monsters suggest the young universe sometimes skipped steps. Now add the little red dots. These objects are compact. Many seem heavily reddened by dust or shaped by dense central light sources. Some researchers have proposed that what we are seeing is not just starlight from a crowded galaxy, but black hole activity wrapped in gas and dust, like a furnace hidden behind a thick red curtain. Canuck's LRD Z8.6 matters because it may show broad hydrogen emission, a classic sign that gas is moving at high speed around a central engine. If that interpretation is right, then this is not just a strange early galaxy. It is the universe caught in the act of building a massive black hole almost immediately. So let me ask you this. Did the early universe grow giant black holes from tiny seeds? Or did it start with heavy seeds almost from the beginning? Pick one before we go further. There is another reason this object hits so hard. The host galaxy may be surprisingly lightweight compared with the black hole it seems to contain. In the nearby universe, black holes and galaxies feel almost negotiated, as if they grew in a tense partnership. Here, the balance may be badly tilted. It is like finding a child wearing an adult heart. The proportions are wrong. And when proportions are wrong in astronomy, they usually point to missing physics. Roberto Maiolino and other teams studying early active galaxies have been pushing on this same puzzle from different angles. Some early systems appear chemically evolved, dusty, and structurally compact sooner than expected. That matters because dust itself takes time to make. Iron, carbon, silicon, these are the ashes of stars. In human terms, it is as if the first campfires had barely gone out, and somehow the room already smells like an old factory. And this is the why now. Webb changed the scale of the problem. Before James Webb, we had hints of extremely early quasars, including monsters seen less than 1 billion years after the Big Bang. But Webb is now revealing a whole population of compact, red, suspiciously mature objects at high redshift. A few anomalies can be dismissed. A category is harder to ignore. If little red dots are common, then Canuck's LRD Z8.6 may not be an exception. It may be a clue that we were measuring the wrong phase of black hole growth all along. Maybe the earliest growth was hidden, dusty, and compact, which means the universe was manufacturing dark engines behind a curtain, while we were mostly looking for bright exposed quasars. That possibility is eerie. It means the cosmos may have spent its first few 100 million years building invisible predators before most galaxies had finished becoming themselves. But wait, there is a twist that makes this worse, not better. If the black hole in this object is real and already this massive, then the problem may not be black hole growth alone. The problem may be galaxy assembly too, because the host did not just fail to keep up, it may have started behind. In other words, maybe the earliest black holes were not passengers inside galaxies. Maybe in some cases, they were the construction bosses. Their gravity pulled gas inward. Their radiation reshaped the surrounding cloud. Their outflows may even have regulated when and where stars could form. We often tell the story as galaxy first, black hole later. Can't Titanic's LRD Z8.6 hints that, at least sometimes, the order was much messier. Can you imagine that reversal? The darkest object in the system acting less like a parasite and more like an impatient architect? I will be honest, that idea is hard to shake once it lands. There are still real uncertainties. The exact black hole mass depends on how we interpret the spectrum. Dust can fake age. Geometry can fake brightness. A dense starburst can imitate some of the signatures of an active nucleus. Astronomers know this. They are not claiming certainty where none exists. But that is exactly why this object is so valuable. It survives skepticism better than most. The case is not built on one dramatic pixel. It is built on redshift, compactness, emission features, and the uncomfortable ratio between central power and galactic mass. And the timing remains the immovable wall. 570 million years is not much. On Earth, that is shorter than the gap between the first complex animals and us. In cosmic terms, it is barely enough time to clear your throat. Yet by then, something in this system may already have become millions of times more massive than the sun and started eating. If that timeline feels almost offensively short to you too, leave a like. Just that number alone, 570 million years, is enough to make the whole early universe feel less orderly than we wanted. I think that is the deeper payoff here. This is not only a story about one object. It is a story about how quickly complexity can appear when the conditions are extreme enough. We talk about cosmic dawn, as though dawn is gentle, soft light, slow unveiling. But real dawn, even on Earth, can be violent. Temperatures jump, shadows vanish, life scrambles to respond. Maybe the universe had a dawn like that too. Not calm, crowded, competitive, full of systems racing to become impossible before the clock said they should. And if that is true, then giant black holes were not late-stage monsters waiting for mature galaxies. They may have been among the first successful products of chaos. Not the end of the story, one of the opening moves. The reason Canucks LRD Z8.6 matters so much is that it turns an abstract debate into a deadline. You can argue about models all day. Light seeds, heavy seeds, super Eddington bursts, direct collapse, mergers. Fine. But this object just stands there, red and compact, asking one rude question. How did the universe run out of time so fast? Personally, I do not think the most unsettling possibility is that our numbers are slightly off. It is that the early universe may have been better at building extremes than we are psychologically prepared for. We like a cosmos that earns its monsters slowly. Canucks may be telling us it did not. And that is why a tiny red speck in Webb's images can feel bigger than a galaxy. Because hidden inside it may be evidence that the darkest engines in the universe were already waking up almost as soon as the lights came on. If early universe mysteries like this fascinate you, subscribe. This channel is for people who like their sense of cosmic order disturbed. Carefully, honestly, and with evidence.